Hi there, this is Liu from NC State University. Today, I will introduce our work on quantum circuits for dynamic runtime assertions in quantum computation. We start from the motivation of this work. Superposition and entanglement are used extensively in quantum programs, and they are fundamental reasons for the computational advantage of quantum computing over classical computing. But superposition and entanglement do not have correspondence in classical computing, which makes them hard to reason about. Assertion is an important technique for debugging programs. However, asserting quantum program is challenging for two reasons. First, a qubit cannot be copied. This is also referred to as the no cloning rule. Second, when a qubit is measured, its superposition state collapses into a classical state, losing the inherent parallel information. Prior work on statistical assertion proposed assertion approaches by measuring the qubits at breakpoints for many times. For example, in the right-hand side of the screen, we can find a test program with classical and superposition assertions. The prior work studied common types of bugs in quantum programs and proposed three statistical assertions, including classical, superposition, and entanglement assertions. The first limitation of the statistical approach is we need to measure the qubit at certain breakpoint. Each measurement stops the execution of the program, and you cannot assert at runtime. The second limitation is since it is statistical, it requires ensembles of runs when the actual computation results are to be measured. To address these two problems, we propose our circuits for dynamic assertions. The dynamic assertions can be used as debugging primitives and as opportunistic error detection for improving the success rates of NISQ systems. Similar to the statistical approach, we propose assertions for three types of states. The state-of-the-art quantum computers only supports measurement at the end of the program, so we need ancilla qubits to measure the states non-destructively while the program is running. The key idea of designing these circuits is to keep the ancilla qubits unentangled from the qubits under test. When they are not entangled, measuring the ancilla qubit will not change the state of the qubits. Here's our circuit for asserting classical state 0. If the qubit state psi equals to the classical state 0, then the output 2-qubit state psi 2 equals to 0 tensor 0. The two qubits are not entangled, and when we measure the second qubit, we will always get 0, which means no assertion error. When the qubit state psi equals to a classical state 1, the output state is 1 tensor 1, and when we measure the second qubit, we will always get a 1, which means assertion error. And if it is in the superposition state due to a bug or runtime error, then psi equals to A0 plus B1, and the output state psi 2 equals to A00 plus B11. When we measure the ancilla qubit, if there is no assertion error, the qubit under test will be projected to the correct state. And the probability distribution of assertion errors can be used to estimate A and B if needed. The second type of assertion is for superpositions. It is a common practice to use Hammer gates to set the input states in the uniform superposition state. So we designed the assertion circuit for uniform superposition state. If the input state is in this uniform superposition state, the plus state, then the output state will be plus tensor 0, which means no assertion error. And when it is in the minus state, which is orthogonal to the plus state, we will always get an assertion error, when measuring the ancilla qubits. And similarly, based on the probability distribution, we can estimate the coefficients A and B. We also introduced the circuits for arbitrary superposition state. Based on the state psi we want to assert, we can find a unitary matrix such that psi and the orthogonal state psi prime are its eigenstate with eigenvalues 1 and -1. We can construct the assertion circuit with a controlled U gate and 2 Hadamard gates. If the input state is psi, the output state would be psi tensor 0. And if it is orthogonal, and we can detect that with the assertion error. So we also find that based on this design, we have another circuit for uniform superposition state assertion, which is shown on the right-hand side of the screen. So the last type of assertion is entanglement assertion. If we want to assert the states with even numbers of 1, we need to initialize the ancilla qubit to 0. And if we want to assert for the state with all numbers of 1s, we initialize the ancilla qubit to 1. When measuring the ancilla qubit with no assertion error, the asserted state is projected to our desired entangled state, which is A00 plus B11. We'll show an example for debugging quantum programs with our assertions. We augmented Qiskit with a function to insert assertion circuits and check ancilla qubits for assertion. We offer 3 kinds of assertion function, which is similar to the statistical approach. The qubit list argument is the list of qubits for assertion, and the face dictionary argument is a dictionary that contains superposition state information for each asserted qubit. Here is the program for quantum phase estimation. Quantum phase estimation estimates the phase of a unitary operator U. In this program, we can insert assertion at 4 different places. First, a quantum algorithm begins with initializing all the qubits to the preconditions in the initialization stage. Usually, the qubits are initialized to classical value or a uniform superposition of values. We can assert these preconditions using classical or superposition assertion. As shown in line 17, we assert for the uniform superposition state using the superposition assertion function. We can also assert at line 23 the ancilla qubit, which is in the non-uniform superposition state psi. In quantum phase estimation, after applying the inverse QFT, the output states of the qubits are in the classical state. We assert for the expected classical states using the classical assertion function in line 35. Besides the desired output, we can also assert for deallocated ancilla qubits used in the algorithm. Line 38 shows the superposition assertion for deallocated ancilla qubit, which ensures that this qubit remains the same as its initialized state. We can think of the noise in quantum computers as program bugs and use our assertion circuits to detect these unexpected changes in our circuits. We use assertions to filter out the erroneous results and get an improvement in the success rate of the circuit. Since the assertion circuit will also introduce noise, we collect the probability of false positive cases and fidelity for all assertion circuits. As we can find in the table, the false positive probability is pretty low, and we expect that the circuit under test to have many more gates and more qubits, which would have much higher error rates compared to the assertion circuits. One of the case study is the quantum Fourier transform circuit. Quantum Fourier transform is a part of many quantum algorithms, including quantum phase estimation and Schur's algorithm. So the output state of quantum Fourier transform can be an output state of the whole program or an intermediate state of the program. We can assert the output state of quantum Fourier transform to improve the success rate. As shown in the table, the success rate without assertion is 72%. When we apply the assertion, we filter out the erroneous results. So the total count changes from 8,192 to 6,909. The success rate improves to 84%. We can not only assert the output state, but we can also assert the ancilla qubit. The ancilla qubit is supposed to be prepared in a classical state or a superposition state and should not be changed during the program execution. So we can leverage the assertion circuit to assert the ancilla qubit. Here is an example of the Bernstein-Vazirani algorithm. The ancilla qubit should stay in a minus state, and if there is error in the program, and they might propagate to the ancilla qubits, so our circuit has a chance to detect these errors. And we find that the success rate improves with the assertion. We also change the circuit size and find that for different size of Bernstein-Vazirani algorithm, the success rate all improves with our assertion circuit. The third case study is about the entangled state, and we use the entanglement swapping protocol as an example. Initially, we have two pairs of entangled qubits. A is entangled with C1 and B is entangled with C2. The entanglement swapping protocol swaps the qubits, and after the swapping process, A and B gets entangled and C1, C2 also gets entangled. So we can apply the entanglement state assertion at two different stages, the initialization stage or the output stage. When we assert at the initialization stage, since the initialization circuit is shallow and there isn't enough errors to be filtered out, the success rate drops after the assertion. In contrast, the success rate after asserting the output state is 56%, much improved to the no assertion case. So, in conclusion, we propose quantum circuits to enable dynamic assertions for 3 states. These circuits enable a dynamic debugging primitive driven by a programmer's understanding of the correct behavior of the quantum program. We also show that the assertion logic can be used in the NISQ systems to improve success rates by filtering out erroneous results. So that's all about my presentation, and thank you for listening.